Designing a system at the end of the day means that we have a task that has to be accomplished. Now, we can see a task as a set of instructions that have to be executed. Just to keep it simple, what if we're going to have 3 multiplication that have to be executed? That means that if you're going to execute these 3 multiplication on a general purpose processor, we have an instruction set that we're going to use, and we are fixed in number of resources that can be used to execute those 3 multiplication. What if we are going to execute on an ASIC? Again, it's somehow easy because we are constrained by the way in which the ASIC has been implemented, and we know how to map those instructions onto the resources that are available in the system. So we are starting from a problem where we're going to have a task that in our example is made of 3 multiplication. Now, we know that with the FPGA, things are different. The FPGA is a game-changing technology. And the reason is quite simple. It can be seen. And the way in which we are going to show it is by drawing a chart. In this chart, we're going to have here the performance on the epsilon axis. And we can consider performance as the overall execution time. Overall execution time. On the x-axis, what we are going to have are is the area of our chip, or if you prefer, the number of resources that we are going to use in order to implement our system that is going to be used to implement that task. So here we're going to have number of resources. Obviously, as we know, resources on an FPGA are different. We can have a lot of different blocks that are going to be used. Just to keep it simple, we're going to consider just one of them. So generally speaking, are the resources used to implement the task. Now, 3 multiplication. What we can have is something like, we are going to execute all the 3 multiplication in parallel because we do not have any data dependency in between them. That means that we can execute them in parallel. In terms of resources, where the resources of 3 in parallel is quite high. What about the performance? Well, if the 3 multiplication are going to be executed in parallel, that means the overall execution time is the time needed to provide the data to the multiplication unit to make the multiplication and then to send back the results. So at the end of the day, the overall execution time is quite low. So this is for the 3 multiplication in parallel. So this is going to provide us a point basically here. A high request in terms of resources and a very super efficient architecture. Now, what if we're going to have something different? And in saying this, I mean that we may not be willing of using all the resources available, so we're going to constrain it. And instead of having the 3 multiplication executed in parallel, we're going to have just 1 multiplication implemented on our device. And in order to be able to complete the task, that means in time we are going to reuse the same multiplication over and over again. So that means that we are quite low in terms of resources, but we are going to be quite high in terms of overall execution time. So this is the case with 1 multiplication unit. So we are somehow here. And now that's exactly why I love FPGAs so much, because nothing of this has been defined. We can play as much as we want with the resources according to our needs. Let's see what I'm talking about. Now, can we do better than this in terms of performance? Which means, can we improve the performance? Well, actually, the answer is no. We cannot do better because that's the best implementation that we can have. So we cannot go lower this line. Now, what about this part of their chart? Can we use less than this amount of resources And the answer is again, no. We cannot use less of one multiplication because otherwise we won't be able to implement our design. Now, can we do worse in terms of performance with respect to the one that we were obtaining with 3 multiplication unit executed in parallel? So can we move up here? And the answer is yes, we can do worse. Obviously, the idea is to try to be as close as possible to this point, but because of communication overhead and so on and so forth, we may have solutions that are going to be somehow here. Now, can we do, in terms of resources, can we move here? Well, again, the answer is yes, but again, do we need to have more multiplication unit? No. So those are unfeasible area, and I would say that this is a kind of useless implementation. So it is not necessary to try to explore anything that is going to be higher in terms of resources, because we are not going to gain in terms of performance, which means that we are going to waste resources. So it's not really useful. What about the performance? Can we do worse than this? Well, obviously the answer is yes. And the reason is, again, as we were having here, so we can have some communication overhead and so on and so forth. So we may have something that here is not going to be exactly here, but is going to be more up here. So this is a kind of the optimal situation that we may have. This is more a realistic situation. Can we do worse? Well, obviously, we can try to lower it, but again, it's not really going to be a great idea. So again, this is not unfeasible, it's just stupid, let's say, because we don't want to have worse performance with respect to what we can get. So this is basically going to define what we may have. Now, with respect to this, can we draw a sort of a line, just to keep it simple, that is going to connect these two dots together? What we're going to have here? Well, let's see it. What is a point here? So what we have here is basically something that is going to tell you, I'm going to play with the resources and I'm going to gain this performance. Well, the kind of thing here is this point below this line? Yes. So that means that this is a kind of the theoretical performance that we can expect with this number of resources. So everything that is going to be below this line is a sort of an unfeasible solution. So we're going to get rid also of this space. What is going to remain is our feasible solution space. That's exactly where we're going to play in order to define our solution. And why are we not just shooting for the best? Well, it's always a matter of trade-off. Being the best in terms of execution time may not imply that we're going to be the best in terms of power, in terms of energy consumption. So we may not be willing to have this number of resources used to implement our task, to accomplish our task, but we're going to lower it. We know that we are going to lower the performance in execution time, but because of an overall scenario, that may be the solution that we want to have. Now, let's see what is going to happen if we're going to add into this scenario the device, the FPGA. The FPGA has a fixed area, which means that a device has a fixed number of resources that can be used to implement a task. Now, what if our device is going to have a certain number of resources that is going to be here? So here we have the device resources available. What we are observing is that with that device, at the best, what we can gain are those performance. That's great, but unfortunately, because we want to play the devil advocate, what we're going to do is, okay, you know what? The performance that we are willing to obtain are somehow here. So that's kind of a bad situation. Why? Because the device is getting performance that are not as low as the one that we are expecting. And in saying low, we are meaning not as good as the one that we are expecting. Remind, overall execution time, the lower is the better. This is something bad, because with that device, we cannot achieve those performance. That's true, that's totally true, but what if we're going to use a sort of a, let's say, virtual device? The virtual device is going to provide us a sort of bigger area that can be exploited. Obviously, those are the expected performance, but this is a virtual device, so this is not something that we are really going to have. It's something that we are willing to have, but that we have not. So what does it mean to have a virtual device? It means that over time we are going to reconfigure our FPGA in order to have more resources available, paying this in terms of reconfiguration time. So now the game is, how big is going to be this reconfiguration time? If the reconfiguration time is going to be as big as this line, awesome, we are done. Because we have a virtual device that is going to imply an overhead in reconfiguration, but it is still going to meet our expected performance. So those are the expected performance. That's great. What if we are not going to be able to find a way in which with the reconfiguration we are going to meet this performance? In other terms, what if our virtual device, let's say virtual device star, instead of having this, is going to have this reconfiguration? Well, that's again something that we are not willing of doing, because it's going to be higher, which means worse performance with respect to the one that we have. So that is exactly where the reconfiguration is coming to play. So let's try to sum up all the things that we have seen. We have the optimal solution in terms of peak performance. We have the kind of sort of worst implementation in terms of peak performance, but we have also a kind of a solution space, a design exploration space that we may have in order to play not just with peak performance, but also take into consideration energy, power, latency, and so on and so forth. So it's not just best, worst, but it's the kind of a solution space that we want to explore in order to have something that is going to be implemented on our device to meet the designer expected performance, the system designer expected performance. What if the expected performance are going to meet, which means the expected performance are going to be here, higher in this graph, which means lower than the one that we can achieve with our device? That's great. That's exactly where the FPGA are going to be useful. We can play in between the worst and the optimal, within the green and the purple point, better than, let's say, the worst and the optimal, and we can configure our device to achieve this performance. What if the performance, the expected performance, are going to be lower than the one that we can have with our device? Not really an ideal situation, but we can try to make it with reconfiguration. So that means that we are going to extend our device, and we are going to gain an advantage in saying that the reconfiguration can take place over time to try to place the resources that were not available in the previous configuration in the time in the future. If the reconfiguration overhead is going to introduce an extension in time, in the overall execution time, that is still going to be below this expected performance line, great, we are done. Otherwise, we are not. Now, just to make it clear, when we are saying that we are going to reconfigure the device, well, the reconfiguration doesn't have to be a complete reconfiguration of the device. We can decide to reconfigure just portion of the device in order to have the extension to define the virtual devices that is going to be needed to gain that performance, to meet that performance. So, not necessarily a complete reconfiguration, it can be a partial reconfiguration of the FPGA.